Hi, I'm Jenna Colson, and I'm an epidemiologist with the University of Notre Dame. On Monday, November 2nd, I'll be joining Alex Perkins, Heidi Beidinger-Burnett, and Marianne McDowell in a discussion about the epidemiology of COVID-19 as part of the Consider This, Simplifying the COVID-19 Conversation series. Today, I'll be presenting some introductory information about the epidemiologic concept of the reproductive number. So the reproductive number, or R, is the average number of individuals that get directly infected by one infectious case throughout the total infectious period for that person. Rnaught, you may have heard of, that value in particular refers to the reproductive number when we're talking about a population where everyone is susceptible, so no one has any immunity to protect them from the virus in the absence of any control activities. So this is the original intrinsic potential of a virus or a disease to cause a spread or an epidemic in a population. So it's the epidemic potential for a specific population for a specific disease. Whereas the reproductive number can also be used more generally to look at any point in time where you can be having interventions, people could be developing immunity. So we can also calculate that. And that can change over the course of an outbreak. And so this is just referred to as the R or the effective R as opposed to Rnaught. So Rnaught has really important implications when it comes to transmission of disease. So 0 is the lower limit for an average number of new cases that come from each case, but there's no theoretical upper limit to how many cases can be caused by each case in a population. The key value to worry about, though, is the value of 1. That's the threshold that's important. If each case on average is only causing one new case, then you're going to get an equilibrium where there's a fairly steady frequency of the disease in a population. Now, if R is less than 1, then you see cases that are going to be decreasing over time. When R is greater than 1, you're seeing an increase in case numbers and the epidemic is going to happen or spread. So the basic components that make up this reproductive number value are C, the number of contacts per unit time, beta, which is just the probability that you're going to have transmission in a given contact, and D, the duration of infectiousness. So the equations can get a lot more complicated, but at its core, these are some of the important ideas. So a contact in this sense is any person that's interacting with our case in a way that could potentially transmit the disease. And each of these components are not just specific to a disease, but they're also specific to a population. So let's look at some individual examples to think about why. So here we have this one sick person. And let's say we're talking about SARS-CoV-2. So contacts in this case would be people who are sharing airspace or touching surfaces after this person when they're sick. So they might have contacts that are occurring at home. So let's say that this example person lives with 3 people and they go to work where they're exposed to a number of potential contacts. Let's say that they socialize at a restaurant and they have contacts that are the people that they're eating with, the wait staff, and people at tables near them. And let's say that there's also just some random contacts that they have either at stores or in public transportation, at the gym, other random contacts in the community. So this person ends up having 43 total contacts over the duration of time that they're infectious. So of those 43 total contacts, now the next parameter we have to think about is what's the actual probability of transmission for each of those contacts, or beta. So you can think that there would be some people that might have really intensive contact. They're spending a lot of time with this person or in really enclosed airspace, very close types of contact. So they might have the highest probability that there would be successful transmission of the virus. And then there might be other people that are a little further away or spend a little less time with the person. And so we'd have sort of decreasing risk as we move outside the circle. So the highest risk people would be relatively more likely to become infected or have a probability of successful transmission, and fewer relatively as we move out of the rings. So overall, this case ended up causing 6 new cases in this example. So let's look at a different person who's going to be causing fewer infections. So let's say that for this person, they only live with one person at home. And in their work environment, they're exposed to only a couple of contacts. And let's say that they don't go to any restaurant, but they do socialize with a group of friends. So 4 contacts in that setting. And let's say that their other random contacts in the community stay pretty consistent. So this person, compared to our original that caused 6 new cases, has a lot fewer contacts, and particularly fewer in that high risk zone. So of their 17 contacts, this example only caused 1 new case. We could also envision a person with higher contact networks. So let's say that in their workplace, this is a person who has more of a customer service or a customer facing job. And so they have more contacts in the work environment. They also attend a big gathering of some kind, maybe a wedding or some other event that's in an enclosed space where they're laughing, singing, talking a lot, or otherwise sharing a lot of their respiratory particles into the air. So our original 2 examples only caused 6 new cases and 1 new case, but this person has a huge number of contacts and a lot more of them in that high risk zone. So in this case, we had 131 contacts and 30 new cases coming from this person. So this is someone that you might hear referred to as a super spreader, or that the event that they attended could be referred to as a super spreading event. It's not necessarily anything about this person's infectiousness, but they did have a much larger contact network, so just more people that could be potentially infected. But the R that's important is the average in a population. So that's what we're going to be calculating, but it's made up of all these different individuals. And it can be influenced by the disease itself, the climate of the area, the types and locations of contacts, the methods of transmission, personal characteristics about the individuals, like are they symptomatic or not, etc. And R is not a fixed value, it's population specific. So it can be higher in dense and highly interactive groups like people in schools or prisons, dormitories, nursing homes, cruise ships, where people have a lot more close contact with individuals around them. You could also think that cities would tend to have higher numbers of contacts than people in rural areas. So the potential spread of the virus would be quicker in places with the higher Rnaught values. So some example Rnaught values are in this table here. The 1918 pandemic strain of influenza, or the Spanish flu, has been estimated to have an Rnaught of 1.5 to 3. Measles is a highly contagious disease. The range of Rnaught values estimated for measles is much higher, tends to be in the range of 12 to 20. But we can also look at SARS coronavirus 1 and seasonal influenza. Seasonal influenza is pretty low, but enough to keep spreading, so in the range of 1.1 to 1.5. The original SARS from the early 2000s, that had an R0 value of about 2 to 3 on average. And depending on the population and the study, SARS-CoV-2 estimates are coming in the ranges of 2 to 6. Remember that our goal is to reduce that R value to be less than 1 in order to slow the spread of the disease and hopefully drive those numbers to 0 to ultimately achieve elimination. R can be lowered and can become lower than R0 in particular through the development of immunity or the implementation of public health interventions that can impact the different components of R. So remember, those components of R include the duration of infectiousness, the number of contacts, and the probability of transmission per contact. We can't really do anything to affect the duration of infectiousness at this point, but we have a lot of interventions for decreasing the number of contacts and the probability of transmission per contact. So decreasing the number of contacts, one of the first things we can do is test and then quickly quarantine and isolate anyone who has been exposed or who has the virus so that they don't have any contacts and can't potentially spread the disease at all. We can also just eliminate or reduce the size of gatherings so that when people find out they're infected, they won't have had as many contacts. And we can practice physical distancing so that we have fewer close contacts. We can also reduce the probability of transmission per contact by using masks, washing our hands frequently, coughing into our elbow as opposed to our hands so that respiratory droplets aren't on our hands to then touch surfaces. We can clean those surfaces frequently. We can have better air filtration or have our contacts take place outdoors rather than indoors whenever possible so that there's more airflow. And we can also look at whether development of immunity in the population reduces the probability of transmission. So in our original scenario, without any interventions in place, our first example person had 43 contacts and caused 6 new cases. Now let's say when we implement interventions, the person is no longer going to the restaurant, but gets takeout instead. So all of those contacts are removed. And let's say they start wearing a mask so that now the contacts have lower risk and move to some of those lower risk circles. And so now, after the implementation of those interventions, we end up with only 23 contacts and 1 new case caused by this person. So if our original example, there were 6 new cases, 1 new cases, and 30 new cases from our 3 set people, now we add interventions. We have 1 case in the first example, no cases in the second example. But it's really important to the population average overall that we have an impact on that super spreader person. So the biggest impact on our population average is going to be if we can affect that person. And that's sometimes talked about in the context of being the dispersion parameter. So we really need to reduce the number of total cases. If they're still at 30, it doesn't matter how much we reduce these other 2 people, the population average is still going to be greater than 1. So if we get those down to 3, all of a sudden we're nearly approaching a population average of 1, and it makes a huge difference. The lower the R, though, the slower the spread of the virus is going to be. When R is approaching 1, we're going to be somewhere in an equilibrium of cases. And we really need to get that R to be less than 1 if we want to move towards having 0 cases in an area. But an important thing to remember is that this value is dynamic. It changes with our behaviors and our responses. And so R will increase again if we go back to normal behaviors and all of our interventions stop before we actually manage to drive cases to 0. So that's all for today, and I hope to see you guys on Monday night when we talk about other aspects of the epidemiology of COVID-19. Thanks for listening.